The most dangerous part of this solar storm hasn't reached Earth yet. The explosion everyone saw, already over. But scientists aren't watching the explosion anymore. They're watching something invisible, something that left the sun in that same eruption. And right now, as you watch this, it is still crossing space, still falling toward us, still keeping a secret that won't be revealed until the final hour before it arrives. And whether it arrives pointing one direction or the exact opposite direction decides everything. Whether the next few nights bring some of the best northern lights in years, or a very bad week for the people whose job is to keep satellites in orbit, planes in the sky, and power grids running. Here's the strange part. Scientists knew within minutes that the flash wasn't the real problem. So what were they actually afraid of? Stick around, because by the end of this, you're going to understand the actual difference between a solar flare and the thing that follows it. And once you see that difference, you will never read a space weather headline the same way again. To understand what happened on June 30th, you have to understand what the sun actually is, not the simple yellow ball from a textbook. A 4.5 billion-year-old ball of plasma over 1 million Earths could fit inside it, and its surface is never, ever still. The sun doesn't burn like a fire. What it has is a boiling ocean of electrically charged gas, threaded everywhere by magnetic field lines, invisible ropes of magnetism, constantly rising, twisting, sinking back down, dragged around by the sun's own rotation. And here's the detail almost nobody knows. The sun's equator spins faster than its poles, which means over months and years, it's quietly winding its own magnetic field into knots. Sometimes those knots break the surface. That's a sunspot, a darker, cooler patch where a bundle of magnetic field lines punches up from the interior. Most sunspots sit quietly and fade away. Every so often, one doesn't behave. That's what active region 4479 was. It rotated onto the Earth-facing side of the sun only days before the eruption, and it immediately raised concern for one reason: its magnetic classification, beta, gamma, delta, the most tangled configuration on the books. Picture hundreds of rubber bands twisted together tighter and tighter around a single point until there's no give left. That's what was happening inside this region. Opposite magnetic polarities forced into direct contact, storing energy with nowhere to go. In the days before June 30th, it had already fired off smaller C-class and M-class flares, distant thunder before the storm actually broke. At 2050 Universal Time, it let go. Here's the mechanism. Two oppositely oriented magnetic field lines forced together by all that stored tension suddenly snap and reconnect into a lower energy configuration. That instant releases an enormous burst of energy, not as heat, but as a flood of light and radiation blasting outward in every direction, including straight at us. That's a solar flare. This one was classified X 1.1, the top tier on the scale scientists use, each letter representing roughly a 10-fold jump in power. Not the biggest the sun can produce, comfortably, unambiguously major. Now think about what 8 minutes actually means. Light is the fastest thing in the universe, and even light takes 8 minutes and 19 seconds to cross the 93 million miles between the sun and Earth. Whatever the sun does, you find out about it 8 minutes later, never sooner. So at 2050 UTC, the sun erupted. At roughly 2058, without warning, that burst of radiation slammed into the daylight side of the planet. High above the surface, Earth's ionosphere, the layer that lets high-frequency radio signals bounce around the curve of the planet, got hit with a surge of extra X-rays. That disturbed the mirror those signals depend on. Picture an airliner on a transoceanic route relying on HF radio, a ship at sea checking in, an amateur operator mid-conversation watching the signal die, all of it across the entire sunlit half of the planet at once. Officially, an R3 event, a strong radio blackout, and then, just as fast, it faded. Signals came back online. If this were a simpler story, that would be the ending. It isn't, because in that same eruption, something else had already left the sun, something slower, something scientists were far more worried about than the flash everyone had just watched. Here's what almost everyone gets wrong about solar storms. They assume the flash is the danger. It isn't. The flash is the warning, the sun announcing that something else might already be on its way. That something is a coronal mass ejection, a CME. This is the idea the whole story hinges on. A flare is light, Light only moves one speed, 8 minutes, always. A CME is not light, it's matter. Billions of tons of magnetized solar plasma physically hurled off the sun, carrying its own mass and momentum across real distance at real finite speed. Even at speeds that sound impossible, it can take anywhere from 15 hours to 3 full days to cross the same distance light finishes in 8 minutes. Think of the flare as a gunshot's flash. Instant, already over. The CME is the bullet, still traveling, still deciding whether it's actually going to hit you. Within an hour of the flare, spacecraft caught it leaving the sun using a coronagraph, an instrument that blocks the sun's glare, the way you'd block the sun with your thumb to see something faint beside it. What they saw was a full halo CME, the cloud expanding outward in a complete ring, the signature of something aimed either straight at Earth or straight past it. Instruments tracking the leading shockwave clocked it near 1,496 kilometers per second. Other instruments, tracking the visible bulk of the cloud from a different angle, measured something closer to 700 to 800. Not a contradiction? 2 tools, 2 angles, 2 different parts of the same structure. Reconciling them into one confident answer takes time scientists didn't fully have, so No A issued a watch, not a promise. A warning that the door was open, G2, moderate, July 3rd. But underneath that watch sat one unresolved question, a single property of this cloud that no instrument on Earth or anywhere near the sun could measure yet. Earth has a shield. Deep in the planet's core, molten iron churns, generating a genuine planet-sized magnetic field, invisible, wrapping the entire planet in what scientists call the magnetosphere. Under ordinary conditions, it deflects the sun's constant, gentle exhale of particles the way a windshield deflects rain. A CME isn't rain, it's a wall. When it reaches Earth, it slams into the sunward face of the magnetosphere and compresses it, squeezes our planet's shield the way a gust flattens a tent against its poles. What happens next comes down to one variable: which direction the magnetic field buried inside that cloud is pointing at the moment of contact. Near Earth's equator, our own field points north. If the CME's field is also north, the two resist each other, like 2 magnets shoved together, same pole to same pole. Most of the energy deflects around us. Some turbulence, maybe a slightly brighter aurora. That's largely that. But if the CME's field points south, the opposite direction, the two don't repel. They lock together. Picture 2 massive invisible zippers swinging shut along a seam across the sky. Scientists call it magnetic reconnection. And once it happens, it opens a direct channel. Energy and charged particles pouring straight into Earth's magnetosphere. That's the entire difference between a storm that fizzles into nothing and a storm the whole planet notices. Here's the part that should genuinely unsettle you. That orientation can only be measured directly by a spacecraft stationed nearly 1 million miles from Earth at a gravitational balance point called L1, an early warning post right at our planet's front door. Even from there, the warning is short. Once the CME's leading edge physically reaches those instruments, forecasters get somewhere between 15 and 60 minutes before that material reaches Earth. Not days, minutes, which means everything else, the imagery, the shock speed, days of modeling, only narrows the range of what's possible. It cannot answer the question that decides everything. Right now, while you're watching this, that answer is already written into the structure of an approaching cloud. It just hasn't reached anyone yet who can read it. So let's say it connects. Let's follow that energy down, because this is where physics turns into something you can watch happen in the sky. Near the poles, Earth's magnetic field lines converge and plunge downward, funneling like the narrow end of a funnel. When reconnection floods the magnetosphere with energy, that energy gets guided along those lines toward the 2 places on the planet where they finally reach the atmosphere. Billions of charged particles come racing down those invisible highways and slam into the upper atmosphere. That collision lights the sky up. Oxygen glows red at higher altitudes, green lower down. Nitrogen contributes the blues and purples along the edges. That's the aurora, a direct visible readout of how much energy just hit us. A G1 might barely reach the northern US on a clear night. The G2 under watch for July 3rd could pull that light down into the upper Midwest, into northern New England and similar latitudes elsewhere. For most people, that's the whole story. Pretty lights, nothing to worry about. but that's only half of it. The same current painting the sky is also moving through the ground, through power lines, pipelines, undersea cables. At G, 2 strength, that's manageable, something grid engineers are trained for. At far greater strength, it becomes something else entirely. And it's not just the ground. Think about who's actually depending on the sky staying calm tonight. Pilots flying polar routes, relying on HF radio where satellite backup thins out. Engineers monitoring low-orbit satellite constellations that carry your phone calls, sitting right inside the disturbed zone. Farmers running centimeter-precise GPS equipment. Grid operators watching their instruments a little closer than usual. Even the astronauts aboard the International Space Station, inside Earth's own shield, watching the same readouts everyone on the ground is watching. Real jobs, real routines, all waiting on the same invisible answer. So far, none of the serious outcomes have happened. No satellite failures, no GPS blackouts, no disrupted flights, no reported impact on the astronauts overhead. What's confirmed is smaller, the radio blackout during the flare, and a stretch of unsettled conditions from earlier CMEs still drifting past. Everything past that stays possible, not confirmed. To understand why scientists don't shrug that gap off, you need to see what this exact mechanism has already done, at its absolute worst. This isn't the first time Earth's shield has been tested. History already answered the question everyone's quietly asking. September 1st, 1859, a British astronomer named Richard Carrington is sketching sunspots through a telescope when the sun does something never formally documented before. A blinding flash of white light gone in minutes. The CME behind it crossed 93 million miles in just 17 hours, fast, which meant it was aimed almost perfectly at us. The world had exactly one piece of vulnerable electrical technology, the telegraph. That was enough. Systems failed across 2 continents. Operators watched sparks jump from their equipment. Some machines kept transmitting even after being unplugged. Running purely on current the storm itself was inducing in the wires. In places, the paper caught fire. The aurora that night was seen as far south as the Caribbean. That event is still the benchmark, not because anyone expects a repeat this week, but because it proves what this mechanism is capable of at its absolute limit. Now, March 1989. A far smaller storm, still severe, finds one weak point, the Hydro-Quebec power grid in Canada. An overloaded transformer takes the entire grid down in under 2 minutes. 6 million people lose power, some for 9 hours, in a Canadian winter. Ask any grid engineer if a solar storm can actually break a power system, and this is the event they point to. The answer is yes, it already happened once. Then, May 2024, a G5 storm, the maximum category that exists, and the first one in over 20 years. Multiple CMEs stacked back to back. Auroras appeared where they almost never do, the southern US, southern Europe. Satellite operators had to actively steer spacecraft to compensate for extra drag. Farmers running precision GPS watched their accuracy drift in real time, and the grid held. Because 1989 taught the engineers a lesson, and this time they had enough warning to use it. Every one of these events ran through the same chain we've been tracing this whole documentary. Flare, then CME, then the coin flip of magnetic orientation, then whatever fell out of that. The event happening right now sits well below all 3. Not a reason to relax completely. A reason to finally understand what the word storm is actually supposed to mean. Which raises the obvious question. Is this normal? Or is something bigger going on? The sun runs on an 11-year cycle, swinging between quiet and violent, driven by that same slow winding of its own magnetic field. We're in solar cycle 25 right now, and it technically peaked back in 2024, but peaks don't switch off cleanly. They drag a long tail behind them, months, sometimes years, of elevated flaring and tangled sunspot regions. What's happening right now fits that pattern exactly. It isn't a sign the sun is doing anything new. It's a sign the sun is doing exactly what it's done roughly every 11 years for as long as anyone has been watching. And this is usually the moment the internet gets it wrong. So let's clear it up fast. Solar storms don't cause earthquakes. There's no mechanism connecting a magnetic disturbance in the sky to stress building in rock, miles underground. HAARP doesn't create solar storms. It's a real research facility in Alaska, and its transmitters are nowhere near powerful enough to influence anything happening 93 million miles away. And no, this won't destroy the internet. The internet's backbone runs on fiber optic cable, pulses of light through glass, and induced electrical currents don't touch that the way they touch copper wiring or long power lines. The real risk is smaller and stranger and far more specific than the panic online usually makes it sound, which honestly makes it more interesting, not less. So where does this actually leave us right now? N. OAA's outlook. Minor conditions, a lull, then the G2 watch centered on July 3rd. The most likely outcome, based on everything currently known, is a moderate storm, a genuinely great night for aurora chasers at higher latitudes, some small temporary technical hiccups, and nothing close to Carrington 1989 or May 2024. Some of the newest analysis even suggests the bulk of this cloud may be angled slightly away from a direct hit, an even softer glance than expected. But forecasts like this can shift right up until the moment of arrival, in either direction. That's not a flaw in the science. That's the science being honest with you. Region 4479 is still up there, still facing Earth, still loaded with enough magnetic tension to fire again in the days ahead. This story isn't over. It's paused. The flash arrived in 8 minutes, but the real story spent days crossing space. And by the time you finish watching this, Earth may already know the answer.